Okay, Science 30. I'm hoping this is going to be the end of the lecture series for this class. I'm going to talk about mass energy equivalence, E equals delta mc squared. And then we're going to talk about some energy innovations. Okay, delta E equals mc squared, right, is change in energies, right? So mass initial minus mass final times the speed of light squared. Okay, so that's an important concept to make sure that we get, so that it's actually change in mass. So when we look at nuclear fission and nuclear fusion, the energy given off by the reaction, we can quantify it. It's the function of the mass of a particle in a reaction and the speed at which they travel. So an object's mass is not related to the sum of its constituent parts. It's also the sum of the total kinetic potential and mass energy it possesses. So this was pretty revolutionary when Einstein determined this. It helped us determine a lot about the wave-particle duality of nature and helped solidify some of the ideas about special and general relativity. But mass has an energy equivalency. So energy can't be created or destroyed, and mass can't be created or destroyed. But mass can be converted directly into energy. Right? So even if the mass changes with the reactants, all of that can be quantified by how much is converted to energy. So a small change in mass equates to a big change in energy because the speed in which the particles are converted to energy is a really big deal. Okay, so E equals delta mc squared. Now this isn't necessarily it's not a super hard equation, but it is quite nitpicky. Okay, so you have example problems on page 514 and page 515 to kind of walk you through these things. But I am going to look at a few problem examples. Now, this is where page number 8 in your data booklet is going to come in handy. So all these values are times 10 to the negative third. So these are the mass energy equivalencies. So how much energy is released per kilogram of each of these atoms. And so we're going to use these values to look at E equals delta mc squared. Okay, so let's take a look at page 516. So the question is asking, calculate the change in mass and corresponding energy change per mole of uranium-235 in the nuclear reactions given. Use masses given in the science data booklet and those provided in the following table. So here's a couple fission equations, and we're trying to find E equals mc squared. So here's the deal, though, is we need to find the change in mass of all of these molecules. This is the tedious part. Okay, so if I look at, again, page 516, numbers 30, let's do 38 and 39. So these aren't hard, but they do take some time. I'm going to do A for 38, and you can do B. Okay, so we know that, so if I look at 38A, we're trying to find change in mass and corresponding change in energy. So we need to find delta M, and delta M is the mass of the reactants minus the mass of the products. Okay, so mass of the reactants minus the mass of the products. Okay. So in this, so what I need to do is I need to find the mass of the reactants first. And the mass of the reactants is the mass of one neutron. So the mass of a neutron plus the mass of uranium. Okay? So I have the mass of one neutron, and that is on my data booklet. And it's 1.00866 times 10 to the negative third. 1.00866 times 10 to the negative third kilograms per mole. Plus the mass of uranium. And that is 235.04392 times 10 to the negative third kilograms per mole. Okay, so that's the mass of the reactants. So let's add that together. So that's what we've got, plus 235.04392 negative 3. And that is 0.236. So significant digits, and again, this is tedious, but significant digits are important for mass equivalency because such small numbers create such a big change. So you have to consider the scale here. So normally I'm not super concerned with significant digits, but things to a decimal make a big difference with delta E equals mc squared, because such small changes in mass make such large changes in energy. So that's my mass of my reactants. Now let's find the mass of the products. Okay, so let's find the mass of the products here. The mass of the products for this question, I have 2 neutrons. So it's 2 times the mass of a neutron plus the mass of strontium. That should be little r, but whatever. Plus the mass of xenon. Okay? And then it's going to be, and delta M is going to equal the mass of the reactants minus the mass of the products when I get this all together. So this is going to be 2 times 1 point, again, I'm going to get this from the data booklet, 1.00866 times 10 to the negative 3 kilograms per mole, plus strontium is 93.91529. There's only one atom, times 10 to the negative 3 kilograms per mole. And then the mass of xenon is 139. 0.91843 times 10 to the negative third kilograms per mole. And I'm going to get the mass of the product, so I'm going to add all that up. So I'm just going to do this in a few steps. I get my numbers confused easy, so I want to make sure I've got everything. 21732 plus 93.91529 times 10 to the negative 3 plus 139.91843 times 10 to the negative 3. Okay, let's add them all up. So plus 0.91529 that should be 0.23585,104 kilograms per mole. Okay, so you can see that the mass of the reactants is greater than the mass of the products. So that energy that mass was lost is converted directly into energy. Okay, so that's what we're looking. So that's the change in energy is what we actually measure when we solve for E equals mc. The change in mass is what we're actually using to solve for the energy released with E equals delta mc squared. So delta m equals 0.23605,258 kilograms per mole minus 0.23585,104 kilograms per mole. So delta M is going to be 0.23605,258 minus, so it's not hard, you just have to make sure that you pay attention because you have to use tedious numbers. Okay, and so what we get is 2.0154 times 10 to the negative 4 kilograms per mole. So that's my delta M. So when I solve for, again, A, this 38A, page 516, this is going to be, so it's actually, so I have the mass change, so that's my mass change. Now I want to solve for the energy change. So E equals delta mc squared. So my energy is going to be in joules, right? And then this is going to be 2.0154 times 10 to the negative 4 multiplied by the speed of light. 3.0 times 10 to the 8th meters per second, and that is going to be squared, right? So 3.0 times 10 to the 8th squared, right, is 2.0154 times 10 to the negative 4, and that's 9.0 times 10 to the 16th. Okay, so let's multiply that, 2.0154 multiplied by 9.0 times 10 to the 16th, and I get 1.81386 times 10 to the 13th joules. Okay. And that's how we use E equals mc squared. So you can see there's a massive amount of energy released for a very small mass change. Okay. So you can do B, and let's look at 39. So number 39 says, calculate the change in mass that would correspond to a release of 2.0 times 10 to the 14th joules of energy. So this is E equals delta mc squared. So I know that I have 2.0 times 10 to the 14th joules of energy. It wants me to solve for delta m. And I know that I have 3.0 times 10 to the 8th squared meters per second for the speed of light. So mass change, this is going to be 2.0 times 10 to the 14th joules. Delta m times 9.0 times 10 to the 16th when we square the speed of light. All right, and then solve for delta M. So delta M equals 2.0 times 10 to the 14th joules over 9.0 times 10 to the 16th. Okay, so this will be an answer in kilograms. Okay, and then this should be about 0.002. 0.002 repeating kilograms. All right. So that's E equals mc squared. Okay, so that's most of the math that you need to know. One last thing that you should look at is nuclear fusion. Right, so it's a process in which two smaller nuclei join to form a large nucleus with a release in energy. Fusion doesn't really happen on Earth in a controlled manner, but it is the primary source of energy of the sun. We need really, really high temperatures for fusion to occur, upwards of 15 million degrees Celsius. It's really hard to simulate that on Earth. Okay, so fission and fusion are renewable sources of energy. Fission's kind of a prototype sort of nuclear reaction till we can figure out fusion on Earth. So fission is a nice start, but what we really want is fusion. I'm going to talk, the last part of this unit is about what sustainability means, but I'm going to go to your textbook. Really quickly, page 517, number 40. This is asking for energy change. This is asking for delta M, and E equals delta mc squared. So you need to do the same thing that I did for 38A for these equations 40A and 40B. Remember, you don't need to use the gamma because there's no mass. So fusion, this is building, so I'm going to show you a fusion equation. So let's look at 40A. So this is page 517, number 40A. Okay, so we have two hydrogen isotopes, and we make a neutron. And then an unknown. So it told you that it's fusion, okay? So this is the main reaction that occurs in the sun. Different isotopes of hydrogen come together to make helium. So I have two protons on this side, so there's no protons here because it's a neutron. So this has to be 2, right? So 2. And then there's one nucleon that's accounted for here. There's 5 on this side, right? So we have to have that. So A, right? 1 plus A. So A has to be 4, right? So 4, 2. So when I look on my periodic table, that's going to be helium. And that is a fusion equation. Okay, so it's the same thing as... You're making sure that the law of conservation of mass and energy is maintained on both sides of the equation. There has to be the same amount of protons on both sides of the equation. There has to be the same amount of nucleons. Okay, so that's fusion. So fusion is the ultimate energy resource in sustainability. Unfortunately, the grade 12s that we're planning, that we're hopefully going to be able to go to Scandinavia this year, we're going to talk about sustainability. Well, we were in Norway, Denmark, and Sweden, but we aren't going, obviously, so this will be a poor replacement for that. So the last part looks at sustainability, so I'm going to look at some sustainable types of energy production. for the last little bit of this lecture, and then that'll be it for Science 30. So what sustainability means. So sustainable means capable of being maintained at length without interruption, weakening, or loss of essential characteristics. All right, so you can sustain something at its current state essentially forever and nothing is compromised. So sustainable development is a development of natural resources that meets the needs of the present generation without compromising the ability of future generations to meet their own needs. So when we say that the oil sands are unsustainable, they are unsustainable because they are not an unlimited resource. They are a resource that will run out. So even though they give us profitability and wealth right now, they will not be something that we can rely on in the future, and that is a fact. That's why we would consider it unsustainable. All right, we live beyond our means of what the earth can handle right now because we use non-renewable resources. So sustainability is not just an ecological thing. Obviously, ecology is a big pillar of that. Okay. But they're all related, right? We want to be able to, if we can sustain environments, then we can sustain cultural integrity, right? We also want to be sustainable politically, right? If we don't have environments that can sustain the human species, then we run the risk of falling into disorder, and that's why we need democracy. Okay, and we also need economic sustainability, right? So all these things are intertwined, and we're really worried about economic sustainability right now because of this pandemic, right? We haven't been preparing for this, and so as a result, we're kind of in it really shows how unsustainable our economy is based on the current state that we're in, right? So future planning needs to take that into consideration. We're particularly feeling the burn of that in Alberta because we're so natural resource based, and there's no demand for oil right now. So we need to have other alternatives. So diverse economies are more sustainable, right? Right. So this is helps you figure this out on page 527, 528. But I've summarized that on the in this slide as well. So ecological sustainability means functioning away as to not adversely affect air, water, land, biodiversity, or natural ecosystems. Societal sustainability is the ability of a group to support adequate living standards for its members. And you can see housing, healthcare, respect, and maintenance of cultural values. Economic sustainability is the ability to provide employment opportunities and have access to goods and services in a manner that does not decrease availability of natural resources. So some types of sustainable energy resources that we should be kind of investing in over the future. I'm going to discuss a few of them, and then that will be it. This will help you do your assignments and help answer the last few questions in your energy and environment booklet. So geothermal energy is heat originating from radioactive decay in the Earth's core. It works on simple thermodynamics. And the ground houses a certain amount of geothermal energy in comparison to the air, right? In the summertime, the air is warmer, and in the wintertime, the air is cooler than the ground, right? So in the summertime, you will have heat being transferred from the air into the ground, and then it's the other way around in the winter. So it works on thermodynamics. Right, so decays of radioactive isotopes maintains the Earth's innermost layer at 5,000 degrees Celsius. This drives convection currents. Right, so areas that are really geothermically active, like Iceland, where there's surface volcanoes, they can do a lot with geothermal. There's a lot of geothermal in Alberta, a lot of geothermal capability in Alberta, but you don't necessarily need to have seismically active areas where there's magma and lava coming up through the mantle. You can use the temperature difference between the land and the air locally as well to put in geothermal heating in your house. You put in lines in your house, and right. So this is a geothermal system here, and you use solvent liquids to transfer heat. Right, so with an Earth energy system, household geothermal, you have a loop of piping through the ground that absorbs thermal energy. So the ground temperature is constant year-round because it's shielded from the environment. So that keeps it warmer in the winter when the air is colder, so heat gets transferred from the ground to the air in your house, and in the summertime it's also cooler. So that transfers warm air from your house into the ground. Okay. So the startup cost for geothermal is a little bit expensive, but over its lifetime it pays for itself. We can also use tidal energy. Now, not every area of the world can use this because you have to have an area that has large tides, obviously. So a tide is the deformation of land and water due to the gravitational fields of the moon and the sun. Water is constantly moving as a result of tidal forces. So the moon creates a tidal bulge in the shape of the Earth, and this draws water and land closer to the moon, where the moon is nearest, and then it pulls the Earth and water away from the moon on the side furthest away from it. So this causes water to move and deform. Okay, this happens twice a day, right? There's 2 tides a day. So where there's large tides, that's great. You have to have the land to deal with this too. So like places like the Bay of Fundy in New Brunswick, the tides are really prominent because of the way the elevation changes in the actual ocean bottom there. It's a very good place for tidal energy. So this is a tidal generator. As the tides move in and out, they turn a turbine. Alberta is a very good place for solar energy. You could buy a solar kit which gives you 6 kilowatt hours a month for as low as $10,000 now. Right, so Alberta gets lots of sunlight, so it's quite a good place for solar. But you don't necessarily need to have solar panels. You could use passive solar. So if you have intelligent home design, right? Depending on where you put your windows or where you choose to put your deck and where you choose to open your windows, you can design your home so that heat is absorbed and then it's maintained inside the house. So that's called passive solar energy. You're not actually using solar panels. You could also have solar heat collectors and solar panels, right? So we can use mechanical devices so active solar technologies, right? So we can absorb solar energy and convert it into thermal energy. You could use a solar heater in order to heat your water tank at home. Or you can use full-blown solar panels, which have photovoltaic cells, right? So solar energy is converted into electrical energy, and then we'll use that for mechanical energy. So electricity will be used for something. So we create moving electrons in the voltaic cells, right? They could be the nickel cadmium or phosphorus and boron or something else like that, and that creates electrical movement. And then that's how solar panels give us energy. We already talked about hydro. This could be something that you look at with one of your assignments, right? So pros of hydro, right? It comes from the sun. No emissions, right? Water is not polluted or consumed. It returns to the water cycle. It's cheap. Little waste heat generated because you're not actually burning anything. But we're all very familiar with the cons, right? You're damming up a river, right? You're creating reservoirs, subsequent flooding. You change the natural flow of rivers, and we've kind of seen that with salmon runs and things like that. You totally change the environment, right? Rather than fast-flowing water, you have water quality change, yada, yada, yada. So anyway, that's something you can explore further if you want in your assignments at the end of this. This is a salmon ladder on the Columbia River. So this is in Washington State. This is in a place called the Gorge in Washington State. They have a very famous concert hall in the Gorge here. But to deal with these big hydroelectric plants, stopping the salmon run, they built these fish ladders, right? And salmon are now starting to use them again. A lot of the dams have been taken out of these rivers, and then the rivers have been restored to their natural way of flow. But this is a way to get around that if it's impossible to not get rid of. This is a massive dam, right? Sometimes they need to stay in there for various reasons, right? Irrigation is a big deal, hydroelectric, right? So there's lots of reasons why we have dams. Wind energy, right? In western North America, wind moves from warm air masses on the coast to cooler air masses over the prairies. That's where we get very strong Chinook winds. As the precipitation is squeezed out of the clouds as they move up in altitude, they gain potential energy. And when they move back down on the eastern slopes of the Rockies, that potential energy is dissipated as kinetic energy and heat, and that's what a Chinook is. We have wind tunnels that have very, very strong Chinooks, like the Crow's Nest Pass. This is why we have big wind farms in Pincher Creek. Right, they've been known to disrupt bird migration. People get migraines from them sometimes, though, if they're close to them. So they don't come without cost. But the sea train is entirely fueled on wind energy from the Crow's Nest Pass in Calgary. This has a lot of potential biomass. Right, we can take all of our food waste and human waste and turn it into methane and keep it in a closed circuit, or we can use it to create electricity. Right, so rather than using fossil fuels, we can use organic waste from our own refuse and excrement. There is a landfill station in Edmonton that does do this. They harness methane from a lined landfill and create biomass electricity. So plant matter or agricultural waste from recently living sources or waste from living sources that is burned and used as an energy source. Right? Could be carbon neutral if whatever we, let's say there's, excess debris on a farmed field. If it's replanted, it could be carbon neutral, right? If we use wood chips and then replant the trees, it could be carbon neutral as well. This was the debate about using biofuels, right? So getting ethanol from corn, for example, and then putting that into engines rather than having petroleum. So if you have E85 ethanol gasoline, then some of this is coming from crops, and it helps things burn cleaner because there's more oxygen in it. Right, so it requires a lot of land, and it competes directly with us for food resources. So we are affecting the food distribution network by doing this, and that always